Hey folks, this next section in chapter 11, we're going to look back at some more of the graphical solutions. We talked a bit about this in one of the earlier sections. I think 11.1 we did we did at least one graphical solution where we looked at phase lines. Today we're going to do two different kinds of approaches to sketching these differential equations: phase lines and slope fields. And so I'm going to use one example to begin with to sort of play with both of our ideas for sketching. And our focus in this first section is on what we've called autonomous differential equations. Right? And we've talked about autonomous systems that are discrete dynamical systems. So differential equations can also be autonomous. Notice that I might write a general differential equation. I might write y as the dependent variable, x as the independent variable. I might say, well, in general, the rate of change of y could depend on y and x, right? So I'm thinking of y is a function of x, y depends on x, but the rate of change of y might actually depend on y and x. Well, we're making this an autonomous equation by saying x isn't one of the variables here, right? Although this is still true, y is the independent variable, x is still the independent variable and y still depends on x. The differential equation doesn't depend directly on the variable x. It depends on y, which depends on x, but it doesn't directly depend on x. And if that's the case, then we can write dy dx as just some function of y, and that's what we call an autonomous system, and we get equilibrium values, or rest points, when that derivative is equal to 0. So for this example here, the derivative is equal to 0 when y is equal to 0, right? Because dy dx is equal to 2y, and that's 0, and that tells us that y equals 0 is an equilibrium value. And think about why that might be an equilibrium value. If y is equal to 0, then the rate of change of y is 0, so y is not changing, so y stays 0, right? And so that's what I mean by an equilibrium value, or possibly a rest point. So if I've got my x variable and the y variable, what I'm saying is the line y equals 0, I'm going to draw it here in red, that is an equilibrium value. In other words, for all values of x, I'm always going to stay on y equals 0. If I'm ever on y equals 0, the differential equation does not change. Well, the y value does not change if it's ever 0, because if it is 0, the rate of change of y is 0, and say y is 0 for all time. All right, so that's an equilibrium value. Now what we're going to do is think about what happens around the equilibrium value. What happens when y equals 1? For example, if I look at this differential equation, when y is equal to 1, then dy dx is also equal to 2 times 1, which is 2. So when y is equal to 1, now there's a bad sort of graph of the line y equals 1. When y equals 1, what's the slope here? Because remember, this thing is the slope. This is the rate of change of y. So the slope of the curve that solves this differential equation, the slope has to be 2. So everywhere along this line, the slope has to be 2. And so I'm just going to draw a whole lot of lines where I'm imagining these little lines I'm drawing have slope 2. You know, I'm not being real careful about it, but I'm imagining that each of those little line segments that I have drawn have slope 2. Right? They've got positive slope, and I'm imagining that's 2. I know the slope of this line down there is 0. But then I could look at different values of y, right? What happens when y is equal to 2? In that case, the rate of change of y has got to be 2 times 2, which is 4. So everywhere where y is equal to 2, everywhere along here, the slope now has to be 4. So it has to be twice as slopey as that. So I've got to kind of draw some little line segments that are even slopier, right? These are meant to have slope 4. You can see they're steeper than the ones I drew before. And similarly, I could go down and I could think about what happens when y is minus 1. When y is minus 1, dy dx is equal to it has to be 2 lots of minus 1, which is minus 2. So down here at minus 1, the slope is minus 2, so it's decreasing, and the slope should be the negative of whatever I had up there, because that was slope 2. Right? And similarly, when y is minus 2, when the y value is minus 2, the slope is minus 4. You see where I'm getting these numbers from, right? I'm just plugging in the y value in there. And so now the slope is steeper and negative r. So all of these, when y equals 2, you notice I'm drawing all these little line segments along this constant value where y is 2. This is where y equals, minus 2 in this case. But what I can draw through this picture then are what I'm going to call solution curves, because Well, let me draw one more bunch of these slopes. Imagine that the y value was actually equal to a half. Let's go over here and say the y value is a half. Then the rate of change of y, plugging in here, is 1. So I have here, when I've got y as a half, the slope is, well, it's not a very good slope, but the slope's even less, right? It's slope 1, and then it was slope 2 as I went up. And you can see the kind of curves I must have. Imagine the kind of curves that I would get if I drew them through here. When they pass through any of these little things, if I start there, it has to have the slope of that line. But then as it goes up, the slope gets greater. So the curves must look something like that. Really down here, the slope's close to 0. But as I start bending up, the slope starts going up. I know that when the y value is 2, the slope must be 4. When the y value is 1, the slope must be 2. When the y value is a half, the slope must be 1. So I can kind of draw in these solution curves. If I can imagine, I've got some of them that are going to look like this. So I've got a bunch of curves that are possible solutions of the differential equation. By going downwards, I'm going to get the same kind of idea. Oops, that shouldn't go up. I'm going to have the same values, the same kind of curves down here. So these are possible solutions to the differential equation. And so this bunch of little slope lines I've drawn, this is called a slope field. I've just gone through and drawn the slope at different values of y. If you tell me what y is, this tells me what the slope has to be. And then I can draw these blue things that I'm drawing, and I'm calling them solution curves. And those solution curves are possible solutions of the differential equation. Now, if I tell you that I pass through a certain point, maybe I tell you that my solution passes through that point, then the solution curve that I've selected is the one that, well, at least gets close to that point, right? So if I tell you that the solution passes through that green point, then that picks out this as the solution curve that is actually followed in the case if I know it passes through that green point there. So we get kind of an idea of what the solutions must look like. And this is called a solution curve, and this is one way to look at solutions of these autonomous differential equations. And here's precisely that slope field using Mathematica. It gives you the idea. Come back, slope field. In Mathematica, you get the idea by, you can use this little stream plot, which gives you kind of sample solution lines and indicates the slope. And you can see that if I go to some line like y equals 2, you go up here at y equals 2, all of the little lines, all the little arrows at there have the same point. The idea is the little line segments, if I drew the tangent line to the curve at each point, they'd all have the same slope. And that's the idea. You can see the one down here, when y is equal to 0. This graph that we're actually plotting, I'm just entering the function, which is the right-hand side of the differential equation here. Right? So if I'm solving dy dx equals 2y, then I'm just using 2y as the function. And when y is equal to 0, we've got a horizontal line, the slope is positive. The slope is 0. When y equals minus 1, all of these little arrows are parallel to each other when y equals minus 1, along a horizontal line here. They all have slope minus 2. That's exactly what we saw. And so this Mathematica picture really confirms the idea that we had here, which I sketched by hand. It was pretty straightforward. So these slope fields are a simple way to sort of get a handle on what the solutions of a differential equation might look like. It's a graphical solution. It gives us a feel for the solution. It's not going to give us an analytic solution that we can write down. It's not going to give us an equation, but it gives us a feel for the solution. Let's have a look at another way to solve these. So we saw the slope field way to sort of investigate these differential equations. I'm going to have a different approach, and this is much what we talked about in that earlier section. Remember that we've got the equilibrium value here, y equals 0. That's an equilibrium point or a rest point. And I'm going to build some phase lines. And what I mean by phase lines is I'm literally going to draw the y-axis here. Here's the y-axis. Here's y equals 0. And now let's ask, what's the derivative doing? Well, I know that the derivative is 0 at precisely this point, right? Here's the derivative is 0. The derivative is 0 when y is equal to 0. If y is positive, then the derivative is 2 times y, which is going to be positive. If y is negative, it's 2 times y, which is going to be negative. So here's my phase line. In other words, y is increasing when y is bigger than 0, and it's decreasing when y is less than 0. So that's our phase line. Right? I'm going to draw a second phase line, and what I'm going to do now is add on the second derivative, and this is what we did previously, right? So we can write down the second derivative for this differential equation. It's just the derivative of the first derivative, which was 2y. So that's 2 times y prime, right? 2 times dy dx. And so dy dx was 2y, so this is 2 times 2y. And so this is just 4y. And so again, the second derivative here is equal to 0 at x equals 0. Sorry, not at x equals 0, but also when y equals 0. And that's the only potential place where we go from concave up to concave down. So I'm going to draw that on this same picture here, on this same phase portrait. The second derivative changes sign again when y is 0, and when y is positive, the second derivative is positive, and when y is negative, the second derivative is negative. So we get the idea that we can kind of say when y is bigger than 0, y as a function of x, well, it's increasing because the first derivative is positive and it's concave up, right? But when y is less than 0, y is decreasing because the first derivative is negative now, and it's going to be concave down because the second derivative is negative. So we can draw a graph of that. Again, I've marked the line y equals 0. It's an equilibrium value. And be really clear, I talked about this last time, but be really clear on this phase line, I've drawn y values. These aren't x values. These aren't critical points and points of inflection. Those were ideas we had in Calc 1 that were about what the derivatives were doing as a function of x. Now I'm looking at what's happening in y. So I'm looking up here. If y is positive, then I'm on this half of the graph. And if y is negative, I'm on that half of the graph. If y is positive at some point, let's say I start here, then y is going to be an increasing function that's concave up. And so it must look something like that. If y is negative at some point, then it's going to be a decreasing function and it's going to be concave down. And so we can get all the sorts of curves that we looked at before, right, that are going to have this general behavior. So, yeah, that's not very good. Starting lower, it's going to go, and then it's going to increase up this way. And we're going to have other graphs that are going like that. I'm just not drawing all of them, but they're going to have this general kind of behavior, right? If I can continue that one back a little bit like that. So you get the idea of what the solution looks like by using those regions. When y is positive, I know it's increasing function that's concave up, and so I get these kind of curves. And again, these are the solution curves. So this method is called the method of using phase lines, right? The method of phase lines. We get the same kind of insight. It's a different kind of way to look at the problem. Let's have a look at another example where we do this. So here's our next problem. It involves a quadratic, and we want to find the equilibrium points here, which means setting the derivative equal to 0. The derivative is equal to 0 when y is equal to 0 or y equals 4. So let's have a go at sketching. Here's the y values. I'm going to draw a phase line for dy dx. And so we've got these two important points on this line, 0 and 4. And so let's think about what's happening between those points. So between 0 and 4, let's say at 2, I can plug in here and I find y prime is negative, right? Y prime in this region is negative because this is y prime, right? Y prime is just dy dx. So the rate of change is negative in that region when y is 2. So when y is bigger than 4, I know it's 0 here, so this is an equilibrium point, this is an equilibrium point. When y is bigger than 4, like 6, then y prime is going to be positive, right? And when it's less than 0, it'll be a negative and a negative, so it's going to be negative again down here. I think that can't be right. It's going to be a negative, and that makes a positive. So there you go. So to kind of help us, what they do in the book is they say, okay, if this is the first derivative we're looking at, what's happening in the regions? If y prime is positive, that means y is increasing. So if I'm sitting on the y-axis, I'm going to move to the right because this is the y-axis, remember. And so if you give me a y value that's negative down here, then y prime is positive, and so y is going to get bigger. And if you give me a y value between 0 and 4, then the rate of change is negative, so y is decreasing, so we're moving to the right. Right? So this, I can immediately see that 0 is going to be a stable equilibrium point, because if I'm less than 0, then I'm going to move towards 0. And if I'm bigger than 0, I'm going to move towards 0. So y equals 0 is a stable equilibrium. If we're bigger than 4, we're going to move away from 4. And so that gives us a good idea. In other words, another way of saying that is if y is less than 0, then y is increasing, right? And if y is between 0 and 4, then y is decreasing. And if y is bigger than 4, then y again is increasing. And so this is, I'm just listing it out in a different way. You obviously don't have to do it two different ways, but this list of things is exactly what this picture is representing. So I could start doing the picture, but before we do that, let's look at the second derivative, which again is going to take some work because we're going to have to start with the first derivative and take its derivative, right? So the second derivative is the derivative of the derivative. So in this case, we're differentiating. I'm going to multiply that out just for simplicity. We're going to differentiate y squared minus 4y, right? This is y prime. This is just this differential equation. I just multiplied it out. This is y squared minus 4y. And now when I take the derivative, what I get is 2y minus 4. And then I multiply that by, well, I multiply it by y prime. Because I'm using the chain rule, right? This is implicit differentiation. I'm differentiating with respect to x, but these are y's. And so I'm doing implicit differentiation. And when I do implicit differentiation, I pick up a y prime. I know what y prime is. I'm going to factor a 2 out of that just for fun. I know what y prime is. There it is up there. It's y minus 4, right? I'm just plugging in for y prime. That's y prime. So what I've got here is a second derivative with respect to x has a bunch of terms in it. Just rearranging them, it's y minus 2, y minus 4. There we go. There's our second derivative with respect to x. And we've got the first derivative up there because that was our original differential equation. So I'm going to go on to the next page and draw the phase line for the second derivative. Okay, so in this case you see, again, we've got 3 places where the second derivative could be 0. So here I'm going to be dealing with the second derivative, y double prime. The y double prime could be 0 at 0, it can be 0 at 2, and it can be 0 at 4, and we need to look around that. So those are the places that we have to worry about. If y is between 0 and 2, let's say y equals 1, then I get a positive, a negative, and a negative. So that all works out to be a positive, and y double prime is greater than 0 in that region. Between 2 and 4, so for example at 3, I get 6 times 1 times minus 1, so y double prime is negative in this region. And then when y is bigger than 4, positive, 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 so y double prime becomes positive again when y is bigger than 4. And when y is negative, I've got a negative, and a negative, and a negative, so that's negative. So there is my second derivative. And what the book does is actually combine this with the first derivative. So I'm going to break it up into these 3 regions. So that's what I'm going to draw. And I'm going to note that when y is less than 0, y prime is greater than 0. So I'm just copying this information. Between 0 and 4, y prime is negative. So that's these 2 regions. And then when y is bigger than 4, y prime is greater than 0. And that is all we need, right? This information here is all we need. And I zoomed in on it a little bit so we can see it. But now I'm going to use this information to plot the solution curves, the possible solution curves. So let's mark on this the key points. Y equals 0 is one of them, y equals 4 is another one of them, because those are the equilibrium points from our initial analysis, right? When we looked up here, we had 2 equilibrium points, 0 and 4, and you can see those on the curve, right, on the graph. Now, we also have something special going on at y equals 2. We know that at y equals 2, we've got an inflection point, right? Because at y equals 2, I don't know what that shape is, at y equals 2, we go for, it's decreasing, less than 2 and greater than 2, y is decreasing, but we have, I'm not going to call it an inflection point, but we have concavity changing. So let's think about just starting at x equals 0. If I start at x equals 0 but below 2, above 0, if I start at a point down here, what's going on? I'm on the y-axis between 0 and 2 like that. So the function's decreasing and it's concave up. So just to make my picture easier to draw, I'm going to imagine it's there, but it's decreasing and it's concave up, and that means the shape must look something like that. You get the idea. Decreasing, concave up. But if I start a little bit bigger than 2, it's still decreasing, but now it's concave down, right? Now it's concave down. So it's decreasing, concave down, which means we start going down until we get to y equals 2. Decreasing, y eventually gets to 2, but it's concave down, and so at y equals 2 it changes to concave up. And so we go off down like that. So if I started a bit bigger, it might take longer to get to there, and then it becomes concave up. And so you kind of get the idea of what the picture must look like. I can't cross this line, y equals 0, because that's an equilibrium. If I ever hit that line, I stay on that line for all time, so I can't cross it. If I start with a value of y bigger than 4, then it's increasing and concave up, which means the solutions all bend up like this. Oops, not like that, but like that. Right? There's increasing and concave up. If y is negative, then it's increasing but concave down, which means I'm coming up towards that equilibrium point, but again, I can't cross it. I did a really bad job of drawing that. Coming up towards the equilibrium point, but I can't cross it, and so it looks something like that. So this gives you an idea of what the solutions look like, right? I have a bunch of solutions that are decreasing, concave down, that then become concave up, but still decreasing. And then I have a bunch of solutions that are concave, it doesn't look good down there, but are still, that are increasing and concave up in that region. So this gives us, again, a pretty good idea. And, my idea is this continues back here, but it just gets harder and harder to draw, so those curves are between, they don't ever cross the line y equals 4. So y equals 4 here is what I'm going to call an unstable equilibrium, because everything that's near it eventually moves away. If I think about moving in the x direction, things, as you go along the x direction, things are moving away from 4, and yet whether I'm above or below y equals 0 initially, if I'm close to 0, then I'm going to move in towards it. And by close, I mean anything less than 0 is going to eventually head towards 0, and anything between 0 and 4 is, as a starting point, when x equals 0, anything starting between 0 and 4 is eventually going to head towards the equilibrium value at y equals 0. So y equals 0 is a stable equilibrium, and y equals 4 is an unstable equilibrium. And hopefully that gives you some idea how you can use these pictures to get a really good idea of the behavior of these functions without solving the differential equation. Right? Solving this differential equation is actually hard work. It's something that we need Calc 2 skills and we need differential equation skills to be able to solve that. But sketching this graph is actually pretty straightforward. And I could have sketched this graph as well using a phase portrait. So let's have another look at these kind of slope fields. And the idea is, again, pick a point. For example, let's pick the point y equals 4. When y equals 4, there's the slope, right? This thing is precisely equal to the slope. I'm just drawing the same picture again to show that we're going to get the same kind of idea. If I plug y equals 4 in there, you get 0. So the slope is 0. So I'm going to draw a whole lot of little pieces of tangent line, right? These little pieces of tangent line all have slope 0, or they should have, because that's the slope when y equals 4. When y equals 2, I could plug 2 in here and I'd get 2 lots of 2 minus 4, which sounds, 2 minus 4, that leaves minus 2. So when y is 2, what I'm saying is y prime is 2 times 2 minus 4. It's hard to say it because there's lots of 2's and 4's here, and I think that's equal to minus 4. So this is quite a steep slope, right? The idea is this thing is copied all the way along, and I could just do a bunch of these. Oops, not that one. And so every single one of those is meant to have, on my picture here, every one of those is meant to be a little line segment with slope minus 2. But if I go to, let's say, y equals 3, when I plug 3 in here, I get 3 lots of negative 1, and so it's going to have a slope of minus 3. So it's going to be negative, but not quite as steep as the one before, and they're meant to be the same, right? It's negative, but it's not quite as steep as the one before. And so here's a whole bunch of them, and each of those has slope minus 3. But what about I plugged in y equals 1 into this? If I plug y equals 1, again I get minus 3. So the line down here, all the points should have the same slope as they did up there. And so you start to get an idea what it looks like. When y equals 0, if I plug that in, all of the line segments will have slope 0. So I get a whole bunch of line segments along here with slope 0. And so that starts to give us an idea of what this looks like. Let me pick another point. Let me pick y equals a half. If I plug a half in up here, I get a half y prime when y equals a half is going to be equal to a half times y minus, a half minus 4 which is a half of, well, in the brackets I've got 1 over 2 minus 8 over 2, so that's negative 7 over 2, so that's negative 7 over 4, so that's just a bit bigger than 2. So it's not as steep as that, so it's going to start looking less steep, right? And so, you know, we had slope minus 3 here, oops, minus 3, but here the slope is minus 7 over 4, so that's actually a little less than 2. And so on. So you can continue doing this kind of thing and you get the idea of what the graph must look like. It's got to pass through that line with slope minus, what was that, minus 3. It's got to get to here with slope minus 4. It's got to come through here with slope of minus 3 again. Then it's going to have a slope of minus 7 over 2 down here. But it can never get to 0, so it's going to head off that way and it'll never cross the line. So we'll have a bunch of solution curves that have that kind of shape. If I start down here, then they're just going to look, yep, not quite that steep, right? They're going to look like that. And so as we draw these things, we're going to get a whole bunch of different solution curves. And you can see that they're all very much like the solutions we did before. If we plotted some up at 5 here, I'd get 5 times 1. So these are all positive and quite steep. That's probably maybe not even steep enough. So they have slope, what did I say? They had slope 5. And so again, there's a bunch of lines with slope 5, and we can sort of imagine that when we're getting really close to y equals 4, the slope's going to be really close to 0, but by the time it gets there, it's got to be 5, and then it's got to be going up. Right? The whole idea of these slope fields is that as I pass 5, the slope should be whatever I calculated here. I think it was actually 5. As I pass y equals 2, each one of these should be parallel to the lines I've drawn here, and they roughly are. I haven't done a terrible job, but here they should be more like that, right? So the tangent line to the curve should match the slope field. That's what I'm doing. So I'm kind of joining in with those purple things. And the slope field gives me a decent idea of how that works. And here's the picture from Mathematica, and you see it very much matches the kind of slope field we drew, where things are going up quickly at the top and then they're coming down, and then I didn't draw the below y equals 0. But this gives you the same idea, where in red I've shown you y equals 0 and y equals 4. And I'm going to put this Mathematica file on Blackboard so you can play with it. And so hopefully you can use that file to explore a bit more what these slope fields look like. They're kind of slow to draw out. The phase lines are kind of cool. Hopefully that makes sense. And I'm going to give you some homework to look on for these. So that's all I got to say today. I hope everyone's doing well. Give me a shout if you've got questions. I'll talk to you soon.